Okay, now we're going to cover the answers for the assigned problems for the Chapter 10 lab. First thing you were asked to do was question 4, parts A and B. So the problem says, one sample has the sums of squares of 60 points, and a second sample has the sums of squares of 48 points. So let's write that down. The first sample has the sums of squares of 60, and the second sample has the sums of squares of 48. Part A says, if we have 7 scores for both samples, find each of the sample variances, calculate calculate the pooled variance. Because the samples are the same size, you should find the pooled variances exactly halfway between the two sample variances. Remember, that works exactly like the weighted mean that we've talked about in the lecture for this chapter that was really touching all the way back to Chapter 3 on the weighted mean. So here we know that this sample size is 7 and this sample size is 7. And the problem said first calculate each sample variance separately. So let's remember the formula for sample variance is sums of squares over degrees of freedom. So over here, our sample variance for the first sample is our sums of squares divided by degrees of freedom. 7 minus 1 is 6, 10 points. And over here, our variance for the second sample is 48 divided by 6, which gives us 8. Well, this is the point at which we could take that shortcut. Some of you like to take it, some of you don't. It's optional. But because both groups weigh the same, they both have 7 scores in them, we could simply get the average of these two sample variances. 10 plus 8, there are 2 variances, so divide by 2. So 18 divided by 2 is 9. Also, just our powers of intellect would tell us what number is exactly between 8 and 10? 9. So that's where we should expect it to be. So we can take the shortcut, but let's go ahead and work it out with the full formula, with the never fail version of how to do this. So remember that our equation for pooled variance is sums of squares for the first sample plus sums of squares for the second sample divided by degrees of freedom for the first sample plus degrees of freedom for the second sample. So we've got 60 and 48 on the top. And we've got 6 and 6 on the bottom. So we end up with 108 on the top divided by 12 on the bottom. So when we calculate that, we find indeed our pooled variance is exactly 9 points, right where it should be. So for part B, what we're going to do is unbalance these groups, make them weigh differently. So for part B, it says now assume that there are 7 scores in the first sample, but only 5 scores in the second. So we're going to need to change this down to 5. And again, it wants us to calculate each sample separately, and then it wants us to compute the pooled variance, that combined variance. And again, it gives us a hint here. It says, again, calculate the sample variances and the pooled variance. You should find the pooled variance is closer to the variance for the larger sample. So in doing this, we can see that, of course, we didn't change anything for the first sample, so it's still sums of squares of 60, still sample size of 7, so 6 degrees of freedom gets us 10 points for our pooled variance. But over here now, our degrees of freedom is down to 4. So our pooled variance, our sample variance for the second sample moves up to 12. And we should find that the pooled variance should be not exactly halfway between 10 and 12, but closer to 10 because it's the larger group. It gets pulled towards the larger group. So we can't take a shortcut here because we don't have evenly balanced groups. So what we need to do is simply change this value down here to a 4. because our sums of squares are the same. 60 and 48 didn't change. This first group still has 6 degrees of freedom, but that one now has 4. So now we have 108 divided by 10. So now when we calculate that out, you should find that your pooled variance was 10.80. And sure enough, that value was closer to 10 than it was to 12. It lands exactly where we would expect it to. So that was for A and B. Next question that you were asked to cover was 8A, specifically just A. We're not dealing with B. Remember, we're always skipping effect size and statistical power and Cohen's d and all that good stuff. So any questions you ever see with that stuff, remember, we're never doing any of that until probably the very last semester. So 8A, I won't read the whole story problem out to you. You've read it already. But it says use a two-tailed test with an alpha level of 0.05 to determine whether the mean number of calories after the posting is significantly different than before calorie content was posted. So remember, when we're asking if things are just different, not are they better, not are they worse, not are they higher, not are they lower, just are they different, that always means a two-tailed or a non-directional hypothesis test. So that's how we know this is two tails, because it says simply, or it asks simply, are they different from each other? But it doesn't specify different how. So for step 1, our alternate hypothesis is that the difference between the first treated population mean and the second population mean will not equal 0. And the null hypothesis is that the difference between the first treated population mean and the second population mean will equal 0. So again, for our two-tailed test here, that's the only way to write it. It's new, we know from compared to previous chapters, but that's the way we write that out. For step 2, again, we know it's two tails. We know that the alpha level was 0.05. And for our degrees of freedom, remember, we want the total degrees of freedom for the whole study. So degrees of freedom for the first sample plus degrees of freedom for the second sample. And when we look in the problem, it tells us that the first sample had 100 folks in it and the second sample had 100 folks in it. So you can either do 100 plus 100 minus 2 or 99 plus 99. Either way, you're going to get to 198, which is a much bigger number than we're used to seeing. But they're bigger sample sizes, and there's 2 of them. So when we look that up in our critical T table, down to the header for two tails, over to the alpha level of 0.05, down, of course, 198 isn't going to be there, but we have to go to what's closest for it. Our critical T equals positive or negative plus or minus 1.980. So that's our step 2. Next up, step 3, our calculations. So the first thing we've got to get in step 3 is our pooled variance. So again, we've got some choices here, but because both groups weigh the same, we could employ a shortcut or we could do the full formula. But the trick here, of course, is that they gave us standard deviation, and we're not using standard deviation anymore. So how do we convert standard deviation into variance? Well, again, if we can remember the symbols and the names of the symbols, standard deviation is this S, and sample variance is S squared. Well, how do you turn S into S squared? You square it, right? So all we have to do to get our variance values is to square the standard deviation. So the sample variance for the first group The standard deviation was given to us as 85, so it's actually 85 squared. And the sample variance for the second group, again, it gave a standard deviation of 91, so the variance is actually 91 squared. This is going to, of course, give us huge numbers, which is probably causing the vast majority of you to freak out. This can't be right. These numbers are too big. Numbers are just numbers. Sometimes they're big, sometimes they're small. If we're dealing with scores that are close to 100 squared, all our values are going to be pretty big. So just stay calm. Big numbers aren't necessarily wrong numbers. But again, they might just be a little unfamiliar to us. So 85 squared comes out to be 7,225. And 91 squared comes out to be, where did I write that down? 91 squared is 8,281. Oops, not pooled, just for the second group. So we now have the sample variances for each sample. Now we could, again, take the shortcut. 7225 plus 8281 divided by 2, because there's two numbers there, and we would get the correct answer. Or if we wanted to use the full formula, what we're going to have to do is get sums of squares out of this, because the formula needs sums of squares. The formula doesn't use variance. Again, when we look at the formula, it's not about variance, it's about sums of squares. So, let's again look at our formula for variance is sums of squares over degrees of freedom. Well, we know what the variance is now. We know what the degrees of freedom are. They're 99 for the first group and 99 for the second group. So plug in what we know and solve for what we don't. So for the first sample, divide these off a little bit here. For the first sample, we know that the sample variance we know, is 7225. Sums of squares is what we want, and the degrees of freedom is 99. So we cross multiply to get rid of that divisor of 99. And so what we end up with is the sums of squares of 715,275. When we do the same thing over here, we see that 8,281 is our variance. Sums of squares is what we're solving for. 99 is our degrees of freedom. So our sums of squares for the second group, again, cross multiply, the same action. So here we have 819,000 and 819. Now we have the information to actually put into the pooled variance formula if we wanted to do the formula approach. So we plug in our sums of squares values from each side, plug in our degrees of freedom values from each side, and what we find is our pooled variance is 7,753. Oops, 3. Again, we could have gotten that by just averaging these two numbers, but I wanted to show you the formula approach. So all of that was just to get our pooled variance. So the very first part of step 3, this is the very first computation for all of that stuff. So let's get rid of this to make room for the next part. The next calculation we need is for our estimated standard error. So remember, that's our new symbol for that, the amount of difference to expect between two different sample means due to random chance or random circumstance alone. And so here we want our pooled variance divided by sample size plus our pooled variance divided by the other sample size, and then all of that square rooted. Remember, it's two separate fractions here. So we plug in our values. So our our pooled variance was 7,753 divided by 100 plus 7,753 divided by 100, and then square root all of that. So this fraction, that fraction, add them together, then square root. Make sure you get your order of operations down. So when we do all of those calculations, you should find that your estimated standard error is 12.45. So that's our second calculation for step 3. So first was to get the pooled variance of 7,753. Second, to get our estimated standard error of 12.45. Now we can do the third and final calculation for our t statistic. So again, let me make some room here. Sample mean 1 minus sample mean 2 divided by estimated standard error. Remember, this is our simplified version of the equation, which is pretty nice. So the problem tells us that the first sample has a mean of 786. Second sample has a mean of 772. And we know that our estimated standard error was 12.45. So 786 minus 772 divided by 12.45, and our t statistic is 1.12. So not a very large t statistic there, yeah? So remember, back in step 2, our critical t was plus or minus 1.980. Where does 1.12 fall? Right in there. So we are in the body. If we are in the body, if we miss the tail, our decision as always is to fail to reject the null. And again, if we needed to write this in APA format, we would say that we had a t of 198, which equaled 1.12. P was greater than 0.05. So there is our answer to question 8A, or our answers to 8A. Next up for us is 15, parts A and B. Question 15, a researcher conducts an independent measure study comparing two treatments and reports the t statistic as a t of 18 equals 2.15. So we're given a t of 18 equals 2.15. So I don't have to do any math. There's no formulas here. It gave us the t statistic. It's done for us. So part A of problem 15 asks, how many individuals participated in the study? Well, remember that 18 is degrees of freedom. You get degrees of freedom from n minus 1. But remember, there's two groups. We had to chip one score off of the group 1 and one off of group 2. So we've subtracted 2 out of that. So we have to put the 2 back in. So we know that the sample size was 20. And then part B asked, use a two-tailed test with an alpha level 0.05. Is there a significant difference between the treatments? Well, all we have to do is look up our critical T value. So if it's two-tailed, alpha level 0.05, we've got 18 degrees of freedom. We find that our critical T value is plus or minus 2.101. We already know the T statistic was 2.15, so that lands over there. So what's our statistical decision? Reject the null hypothesis. So that's question 15, parts A and B. And then the last part of the lab was for question 18, parts A and B. Question 18. If other factors are held constant, explain how each of the following influences the value of the independent measures T statistic, the likelihood of rejecting the null hypothesis, and the magnitude of measures of effect size. Well, again, we know we don't have to do the effect size part of it, so it's just the two pieces of that. So it's really just mantra questions. And so it says, if A, increasing the number of scores. Well, if we increase the number of scores, error goes down. If error goes down, your T statistic goes up. And if your T statistic goes up, you're more likely to reject the null hypothesis. And B says if we increase the variance for each sample. Well, if we increase the variance, that'll make error go up. And if error goes up, our T-stat goes down, which means we will have a lesser chance. Our odds of rejecting the null hypothesis go down. So once more, 18A and B are just ways of grinding through the mantras again. So there are your answers to the assigned problems from Chapter 10. One more chapter of t-tests to come.